Hey everyone, and welcome to another episode of MIPS Crash Course, a series where we go over the MIPS instruction set and some neat things to do with it. So, what are we going to look at today? So today we're going to look at how we implement this pseudocode right here for a C-like program that basically just computes the quadratic function for a user input of x. So, what are some key things that we're going to specifically touch in this video? It's mainly how we, A, translate something like the volatile keyword in C and C++ into assembly language, and that mainly involves us looking at the other thing that we're going to focus on in the video, which is the data segment and how we can actually interact with memory in MIPS. So, as a quick refresher, what does a volatile keyword do in C and C++? It basically says that a value can't be cached in a register. So when we want to access a value that is volatile, it has to go all the way out to memory. And why do we want something like this? So a compiler can be a little overreaching in its optimization sometimes. And this is specifically in the context of, say, multi-threaded applications where inside of one program, a value may not change. However, when you have multiple threads, another thread or another process even might come in and change that value. And because of that, the compiler doesn't actually know about another thread coming in and changing that value. It's just concerned with, this static code right here. And so it might think that a value is, say, constant, when in fact another process could come in and touch that value and change it. So it might optimize it away. And so a way we can avoid that is by using the volatile keyword that says, hey, if you want to access this, go to memory. Okay, so like I said, this is just going to be a simple computation of ax squared plus bx plus c, and it's going to print out the result. Now, one thing that I'll note at the very beginning is that we're using subprograms again, and so we have those subprograms in a different file this time. And we just have a couple convenient ones. So we have one for printing an integer out that takes a string and an integer and then prints them, and then it returns to the caller. We have one for prompting for an integer. So this will print out a string and then read an integer into the program and then return. And then finally, we have just a quick one to terminate the program. So instead of having to load immediate v010 and then syscall, we can just jump to this subprogram right here. Okay, so let's go back to our main program. So the first thing we're going to do is we're just going to load the address of a prompt, store an A0, and then we'll jump and link and go to prompt. And so what prompt does, like I said earlier, prompt will just take an address of a string as an input in A0, and then it will return an integer read into v0. Okay, and so after this point in the program, we've got our integer x that's going to be the input for that quadratic equation. A, b, and c will all be constants in here that we have stored in memory already. So we can actually just go ahead and store, we can play around with memory even a little bit more. So we'll go ahead and call store word, which will take a value stored at an address, or it'll take a value in a register and store it at the address. In this case, we have a label in memory, x, that's a word, so it's 32 bits, or 4 bytes, and it just has a 0 in it, just as kind of a placeholder. So we'll go ahead and just store our value of x right there. And so if we say forget to maybe prompt the user for an integer, well, we'll just end up getting x as our input to the program. But we didn't forget. We already did the prompt. Okay, so let's see first how we're used to handling basically variables in the MIPS instruction set. So usually when we want to say represent say A, B, or C, we would just do a load immediate. And so we just do a load immediate, say into register T0, and we load in 5 or 3 into T1 or 1 into T2. Now, if you remember from about a minute ago, I said that we don't want to load values into registers because that violates this idea that when we want to get a value, we load it from memory. So in this case, we're not loading anything from memory. So we're already violating what that volatile keyword means. So this is more just a refresher of what we're used to, but not exactly what we want to use. So the second thing that we've seen before is, what if we load something directly from memory? So if we have, say, a string in memory, like we had up here, we loaded the address of that string into A0. But what if we have an integer in memory? So we can load it as well. Instead of loading an address, we'll load a word, right? So word is just 32 bits. So we'll load mem-a, mem-b, mem-c, which are all in the data segment and just have labels. They are a word, they are integers, and they are 5, 3, and 1. So we can just load them directly into registers, say T0, T1, T2. Okay, so that's a perfectly valid way, but this can get a little bit messy the more integers that we say have in a program that we need to keep track of, because do we need 1,000 labels if we say have 1,000 kind of variables in a program? Doesn't seem like a very good idea. So instead, we can just store, say, the first, we can just store, say, a label to the first part of memory, or even if we know that it begins at the beginning of the data segment, we don't even need to store any labels in memory. So that's what we do here. So the data segment is going to start at a specific address. So that's where all of these memory values are going to begin. So remember, we have to store multiple things in memory. We have to store our instructions in memory. We also have to store data in memory. So this text section is going to be at a different spot in memory than our data segment down here. So in this case, the data segment begins at this value right here. So in hexadecimal, 0x10010000. And I didn't just, experimentally find this. This is something that's well defined. So I just looked this up. So it begins at this spot. And you can see that if you go to, say, the execution, and when you actually assemble your program. So let's actually just do that real quick. So let's assemble the program. And you can see that the data segment here begins at this address 0x10010000, and you can even see our text segment begins at a different address. It begins at 0x004000000. I may have missed a 0 in there, but you get the idea. It starts at a different position, but it's a set position. So we can count on that. So what we'll do is we'll load into T3 an immediate value. And this stands for load upper immediate, which means we don't want to load an entire word. There's really no need to, because the lower half of this word, the lower 16 bits, are all zeros. So if there's zeros already, why are we writing them? So we can just load the upper 16 bits with that value, 1001, 1001. And effectively at this point, T3 now stores the very first address of the data segment. So we go down to our data segment. The very first address of our data segment will be this right here, this label to mem-a. So instead of, say, addressing this value of 5 via the label, we can just address it by its address in the data segment, which in the case of mem-a will be the first the very first address of the data segment, that 0x10010000. So we can just do a load word into T0, and instead of a label, we'll just load in the address that's stored in T3, which is this value, this beginning of the data segment. And then don't worry about this 0 out to the left. That just is added on to whatever this address is. So we don't need to add anything. We're at the right spot. So that's fine. So if we want to get to the next constant value, or the next value in memory in the data segment, it is exactly going to be 4 bytes away. So if this begins at 0x10010000, then we need to add 4, which stands for 4 bytes. So every single one of those, part of that address, every single one in that address is going to stand for a byte. So 1 byte, 2 byte, 3 byte, 4 byte. So we add 4 to address the 4th byte, right? So we'll go ahead and just add immediate. So we'll add to this address right here, 4, and then we'll get this value right here. So it'll just be 0x10010004 now. So that'll be the next item stored in the data segment, the next word, and we'll just load that word into T1, and then we'll do it again and load the next word stored at this address into T2. Okay, so we effectively did the same thing as we did using labels, but instead of storing labels, we just used the base address of the data segment. Now this is a bit messy. Now, I'm sure you'd agree with me that this is a bit messy having to do the addition, especially when I already said that this value to the left of these parentheses is added on to that address that we're reading from. So the natural thought is, well, why am I adding in the first place if I can add directly next to the address in the load word? And that's completely correct. So this is just called, in this form, we're doing indirect accesses to memory with registers. So we have a register that has a specific address we're loading from, but we can also do register offset, which means that we'll only store the base value in a register, and then we will just increment the offset out to the left. Now in this case, we're doing something a little bit different. We'll increment that address one more time, and that's because we want to get to this spot in memory right here. So this is at offset 0, offset 4, offset 8, and offset 12 from the base of the data segment. Now, what offset 12 from the base of the data segment stores, it stores an address, and it stores an address to a label. And the address that this is storing, this spot in memory is storing, is the address of this constants label. So we've got a couple more constants here that we could access via their own labels, but we could also access it via a lookup from this spot in memory. And so why would we ever want to do this? Well, not everything can be the first thing in the data segment. You know, if we have tons of different variables in there, we may want to have tons of different labels. And if we have tons of different labels, then how do we know where to find the beginning of say another set of constants? And we can do that like this. So we can store the base of a set of constants in memory as well as the constants. So what we'll do here, going back up, is we'll increment by 4 again to get to that address, and then we will load the base address of the constants label into T4. And then we'll do exactly kind of what we said we were going to do after analyzing this, which is we will just keep the base address of those constants constant, and we will just increment this number outside, which is the offset from that address. So it does effectively the same thing as these additions. Okay, so that's basically going to be the major ways that we can access variables in memory. So we can either A, load them via labels. We can B, load them indirectly by loading addresses into registers and then loading values, loading words from memory. Or we can load a base value into a register and then use an offset to access those values. So let's go ahead and do our computation. Our computation isn't that exciting. So just for fun, we'll load our word back from memory. So we'll do load word, and we'll load a value stored at the address in this label X. So remember, X has a spot in memory, so it has an address. So this just says load into S0 whatever is stored at address X. So we'll load that, and then what we'll do is, since S stores X, we'll do mul x stored in T5, so this is x squared. Then we'll multiply x squared, which is stored in T5, with T0, which stores a. So T0 is a, T1 is b, T2 is c. So we'll just multiply that, and we now get ax squared. Now we'll move on to b. So then we can just do, right here, we'll do T1 and S0. So S0 is still x, T1 is b, so we get bx. And we store it in T6. Now we'll add them together. So we'll add T5, which stores ax squared, to T6, which stores bx. And we'll get ax squared plus bx, and we'll just store it in T5. So we'll overwrite T5 because it's not going to be referenced again. So then we'll just do one more addition, and we'll store it in S1, and that will be T5, which stores ax squared plus bx, and then T2, which stores c. So we've computed our value. Okay, so the reason why we stored in S1 is because, well, we just stored in S1 because we're done with it. So T is generally temporary registers, and then S1 are other registers that we can use. So because we finalize that value, we'll just not put it in a temporary register. Okay, so then what we'll do is we'll just set up for our final print. So here we'll just load an address A0, and we'll give it prompt 2, and prompt 2 just says computed value is, and then there we go. And then we'll go ahead and just move A1 or S1 into A1. So S1 stores our value that we computed, this ax squared plus bx plus c, and then we'll just put that in into A1. And the reason why it's A0 and A1 is just because that's what we specified in our subprogram. So we specified A0 to be the address of a string, and then A1 our integer to print. So again, that's in our utils.asm. And then we'll jump and link to print, and that'll print things out, and then we'll jump and link to terminate, which will exit our program. So a quick side note on these utility functions: you can include subprograms that are defined in another file by just doing this directive.include, and then inside of a string like this, just the name of the file or the path to the file. All right, so let's actually run this thing. So let's assemble it. So we can see we've got our values stored in memory, as well as string stored in memory. Looks good. Okay, so we can go ahead and run this. So let's clear our output, go to the run IO, and let's run the program. Okay, so our first subprogram asking us for a value. So let's give it the value 2 for x. Okay, and it runs all the way through the program, computes a value, and then spits it out. So it gave us a computed value is 22. So we can kind of spot check that in our head. So our A, B, and C values are right here in T0, T1, and T2 still. So our A is 2, our B is 4, and our C is 6. So we can just do this in our head. So 2 times 2 is 4, times 2 is 8. Okay, so ax squared is 8. Then we'll have bx, so 2 times 4 is 8. So that will be 8 plus 8 is 16. And then 16 plus 6 is 22. And hey, our computed value is 22. All right, so that's going to do it for today. So there's our example. Again, we translated this program that was in a C-like language into assembly. We showed off 3 different ways that we can access memory via either directly through labels, by getting the base value of, say, the data segment and then incrementing it to each spot in memory. So we're doing indirect access, or we're doing indirect access through registers, and then we showed this base offset register access using this offset right outside of an address in parentheses. Okay, so as always, if you go to the GitHub page at github.com/coffeebeforearch, we can go to MIPS Crash Course, and we've got videos, links to all the previous episodes, as well as the files used in those previous episodes. Here we have my email if you ever want to get in touch with me, or if there's a specific example that you want. And let's actually push the code that we've been working on. So let's go ahead and do add data segment example full. Okay, and we'll commit that and we'll push it. So it should push, and then we can reload this. All right, here we go. And here we have it. So we have our main file that we did all this work in, that actually runs the program. And then we have our little assembly program that just contains some subprograms for printing an integer, reading an integer, etc. All right, so like I said, that's going to do it. I'm Nick from Coffee Before Art, and I hope you have a nice day.